Today we are going to be taking a huge leap forward, but going into the details of what we are going to be going to do today. So this is going to be our agenda. The steps you can see more or less are same. As I told you last time, that they are pretty standard for almost all the FEA problems you will be doing, and will remain same no matter which platform you're using for doing your FEA. But before going into today's problem, let's first discuss yesterday's session a bit about the exercise and stuff. And as I promised you last time, that I'll discuss a bit about some possible applications of FEA. So we'll go through those for a couple of minutes, and then we'll start doing the actual problem for today. So a brief review of what we did last time. We actually did an FEA problem in which a 2D problem of plane stress, in which we have a finite size of a plate and we had a known diameter hole in the center of it. So we followed through each of these steps required for carrying out the FEA on FEA analysis for that particular problem. I hope most of you were able to do it. Unfortunately, yeah, my apologies for last time, because the session stopped prematurely. I didn't know that it's going to happen. It was kind of overlapped with the next meeting the HPRC had. So that's why it just stopped in the midway somewhere. So I planned to discuss all these things with you in the last session, but unfortunately I couldn't. But since it was shared with you, and the message which was shared afterwards clearly said that you may want to go through these exercises as well on your own. So some of the things which I wanted you to do. In the first line here, I mentioned the files which I worked on. So they are shared there as well. So what you need to do, you need to just unzip this file located in this folder in your own sketch drive, and then you should be able to run the workbench project on your own system as well. So the next things which I expected you to do was to try and refine the mesh a bit, and then compare the results of the two, the refined mesh and the unrefined mesh. If I recall right, we kept the size of the mesh as 0.1 inches. The element size was 0.1 inches, and we'll find the mesh around the hole by 3 times. So I recommend to go to somewhere like 0.08 and 0.075 somewhere, or even 0.05, and see how long it's going to take. I wish you will not run out of the memory you select. I guess we have been using 2 GB memory at the beginning. It should be enough, but if you think that you are running out of memory, don't go anywhere beyond 0.09 or 0.08 then. This exercise was aimed at seeing or appreciating the point that how FEA results are, or the accuracy of the FEA results are sensitive to the mesh size. So this was the purpose of doing this particular exercise. Then there was another thing about symmetries. We'll be discussing the symmetries in detail today as well. So when we are doing an actual experiment in the lab physically, we have to follow whatever the size and dimension of the specimen is. We cannot do some kind of mirroring, or we cannot take or cut corners in the real world scenarios. But in FEA case, we can definitely do that. And in some of the cases, we have to do that because the size of the mesh is so huge that even if you don't take these kind of approximation and these kind of simplifications in your model, it is going to take ages to solve even a simple problem. So it is always a good practice that if you think that the results have some kind of symmetry about any kind of plane, then make use of that symmetry and only model part of this actual geometry rather than the whole thing. So some of I shared this resource with you, which took up exactly the same problem which we did, but making use of the symmetry. So I urge you that if you haven't gone through it yet, then just go over it once again in your own time for your own practice and for your understanding. And the most important part is to compare the results of this while using the symmetry option, and then while you were using the whole geometry on its own. So compare these two things and see how the results are different or they are same and stuff. After that, there are a lot more geometries and a lot more problem specifications outlined in this particular page. So I recommend you to go over these things. So if anyone has tried any of these things and has faced any kind of problems, you can ask me now before we start our today's session.
So just real quick, there are also some other instructions. If you're having trouble copying and unzipping the file, I posted some additional instructions in the first day PDF that has you can open it directly from Scratch training, intro ANSYS, and then save it to your Scratch directory instead of having to copy the zip. So either one will work.
Great. So Christopher, I guess it's easier if you speak up. So Lisa, can we unmute him? Christopher?
You can unmute him also. If anybody wants to say something, they can raise their hand and then we can unmute them.
Where is it? I still have to practice things. All right.
I have a question on the first exercise.
Okay.
I had an issue trying the symmetry. So it worked where I could have the symmetry normal to the y-axis, but for some reason it wouldn't accept the symmetry normal to the x-axis, which I think has something to do with it being a 2D instead of a 3D analysis, but I wasn't quite sure what I was doing incorrectly.
All right, so I assume that you used this, so you started with this geometry, or like you used symmetry option after creating the full geometry?
It created a new one based off of the quarter.
All right, so you created only this quarter, and then you moved on to the mesh, and then physics setup. So in this setup, you were creating the symmetry thing here. So you inserted this symmetry region. So here under the details, so just under the toolbox or the model tree, you have these details option. Okay. So for example, if you are applying the symmetry, if you have selected this edge, so you want the symmetry to be about your, which axis?
It's the x-axis.
X-axis.
Or cool. Normal, rather.
Yeah, normal to this edge. Okay, and so you have to select x-axis from here in the drop-down menu. But when you're applying a symmetry on this bottom edge, you have to select it to be y-axis. So did you do this part? You selected x-axis for this one and y-axis for this one?
Yes. So I did that. The only problem came on selecting the left-handed edge that was supposed to be normal to the x-axis. However, both x and z-axis were in yellow and remained in yellow. It would only kind of turn white if I selected the y-axis, even for the one that should have been on the x.
All right. So are you sure that when you were where it is? Yeah, when you open the model, if you recall that we clicked on the geometry first. Okay. Do you have it open in by any chance?
I can open up real quick.
Okay. So while you're opening it, let me go through the next slide. Does anyone else has any problem or any question related to previous session? All right, so let's move on. So let me start this thing. I don't know why it is set like that. Okay, so it's not like a whole overwhelming list of applications, or like it is not something which compasses all over the areas where the FEA is basically applied. And you may not find this slide in the files I shared yesterday, because like I'm too lazy to put the citations for the images I'm going to be using or the references to it. All right, so one of the reason of using FEA instead of doing any other kind of stress analysis is the complex geometry of the part. So the part you want to analyze for the stress distribution, strain distribution, and how well it carries the load is complex. So it is advisable that, or not advisable in a sense, actually it is easier to go over the FEA analysis rather than doing the hand calculation. So for example, in this image, you can see that we have a lot of curvatures. These things behave like a beam, as well as it has some centrifugal loads on it and stuff. So, and you know that this is some kind of fan, it's going to rotate at a very high radial speeds. So many considerations need to be taken in it. So if you want to do the stress analysis using analytical relationships, it's going to take too long. It's going to be too tedious, and you have to make a lot of assumptions and stuff to actually make your analytical solution to be useful. So FEA are usually used for the cases where the geometry is pretty complex. Another way is that many tasks require a lot of repetition, a lot of iterations to come to a particular geometry and stuff. So for solving these kind of things, if you start doing these repetitive tasks by hand or by using analytical relationships, it takes a lot of time. So it takes a lot of time in the sense that a lot of manpower is going to be required. But what you can do in the case of FEA, that you can automate these operations and let the computer do the job on its own, and you will come up with a refined solution. Another thing which is pretty well known these days, and like people are working a lot on this thing, is digital twinning. So what digital twinning means? Digital twinning means that once we have learned the behavior of a particular system, we try and replicate that system using some FEA techniques or computational techniques. And once we have a digital twin of that actual physical system, now you can run many experiments without actually spending a lot of time and effort and resources on doing the actual real world experiments, rather than you can just do those things in the digital world and using the computations. One of the example which I'm using these days is doing the simulation of metal cutting. So what our aim in this particular exercise is to come up with a procedure to predict the material properties just by looking at the cutting forces involved in a metal cutting operation. So of course, like the data which we are getting out of these experiments, or the real world case experiments, are very limited, and we are not getting a lot of information out of it. But if we make a digital twin of that particular system altogether, then only we start to get a lot of information, underlying information, which was otherwise hidden in an actual case. Hidden in the sense that we know what is happening there, but to do it by hand, or to actually start to measure it in the real world, is not impossible, but complex and tedious. So you can make the digital twins of an actual systems into a computational world, and then you have all the liberty you can muster to actually start analyzing these things or these real world problems in a digital environment. Another application is, as I just said, that there are certain scenarios where it is not impossible to measure things experimentally or in the real world case, but it is pretty tedious and maybe taking a lot of resources in it, and it's a bit harder. So another way which we come up to use FEA is to do RVE analysis, which we'll be doing today. So RVE stands for representative volume element. So what representative volume element is that we have a bulk material, and we know that some of the phenomena occur in it, but what are the, like we know the far field conditions as well. For example, if we are doing a tensile test on a dog bone specimen, we know that necking occurs in the center, and we have far field results like the value of the displacement and the forces. We can measure that. But what is actually happening within that necking region is some kind of void growth. Okay, or we call it ductile failure. So we know that this is happening, but how the void is behaving in a certain environment, in a certain material, if we start, we can definitely do that experimentally, but it's going to take a lot of effort and a lot complex experimental setups. So when we are trying to understand things and decipher some of the phenomena, underlying phenomena happening in a mechanical world, is to do the RV analysis or representative volume element analysis. So it complements the findings of the experiments. We can't say that they completely replace the findings of the experiments. Rather, they just help us or complement whatever findings we had in the experimentation. Another area of FEA analysis is during the product design. So classically, before all this digital world or digital era, things used to happen like there used to be like drawings, and then people used to make prototypes out of it, prototype 1, 2, 3, and so on and so forth, unless they solve the problem which they were looking their product to do, or their product to start to behave the way it is supposed to. But now, and again, it goes without saying that it takes a lot of resource and efforts. So like these days, instead of going through actual prototypes, or I won't say that it has ceased to occur, it still happens, but the number of iteration or the number of prototypes have gone down a lot. So I don't know whether we have anybody from aerospace department. My background is from aerospace as well. I'm basically an aerospace engineer, but happens to be mechanics now, or materials now, whatever. So in the aerospace world, if you go to early 30s and 40s, they used to have 3 and 4 prototypes, okay, before they actually start to do the actual production of a particular design. But these days, prototypes are unheard of. Even the most advanced airliners as A380s has gone through very minimal prototyping tests. Although they have prototyping systems, but there was no, if I'm correct, there was no prototype A380. So I assume as an engineer, without any discrimination, that aerospace industry is like the epitome of the engineering knowledge, no matter from which background you're coming from. So the peaks and the extremes of engineering are touched in a aerospace environment. So if they can do it, the rest of the world can, of course, follow it. So that was a bit of the background about the applications. The most important one will still be this understanding the underlying mechanism thing. And this is something, since we are conducting this thing for materials science background people, this is going to be one of the most important thing, which you may encounter down the line in your careers. So that's why I have picked up a problem from this area, and this is what we are going to be doing today. So Christopher, have you managed to pull it up? Are you on mute? Let me unmute you.
Yes,
Okay.
thank you. I have it pulled up, but if we could also do this, I guess, after the main instruction, if you wanted.
Lisa, do we have any meeting after this? Will we have some time after 1 o'clock?
I think the next meeting is at 2 o'clock.
So
there's
we
an
are
hour.
planned, yeah. So we are planned to finish at 1. So we will have roughly 1 hour in between, or 15 minutes, I'll say.
Works for me.
All right, cool then. But wait a second. If you are stuck, okay. Since we will go through all these steps in the symmetry part today, so probably it will answer your query as well.
Thank you.
Cool. All right, so let's start with the problem specification. So now we enter in the physical world. We are now going to deal a 3D problem. Our problem is no more a 2D one. Rather, sorry. Rather, we'll be tackling a 3D problem today. Wait a second. Yeah. So the problem for today is we are going to create metal matrix composite. So it is going to be a completely fictitious thing. I doubt that something like this actually occur in the real world, but the what do you call it, like the inspiration is taken from a real world problem where we have metal matrix composites which are like stiffened by some kind of hard particles in it. So how we are going to be doing it, and what is the actual geometry which we'll be tackling is going to be a cube. So this cubic geometry, we are going to call it an RVE. So what RVE actually means? So since all of us have background in the materials, all of us has came across a term called unit cell at least once in our studies. So unit cell is a representation of a crystal. So we say that if we start replicating the unit cell in 3 dimensions, we'll come up with the actual crystal. Okay. So RVE, although the scale is not that small, we are not talking about nanometers or angstroms, rather we are talking about micrometers and millimeters in some cases. But what actually is happening, that if we start to replicate this particular geometry in all 3 dimensions, we'll come up with the bulk material. So representative volume element is exactly the same thing in the macro scale, as if my internet connection is unstable. Why is that? Is my video or screen sharing has some issues, or all of you can hear me well?
There was a little
Because
bit
I'm getting
up and down on the volume, but you have not cut out, and I can still see your screen.
cool then. All right. So that's the important part. All right. So what I was saying. Yeah. So think of RVE as unit cell of a macro scale material, and which is not necessarily as a homogeneous thing. So in case of unit cells, everything is homogeneous. But in case of RVE, it is not necessarily has to be homogeneous. Rather, it has to be representative of all the non-homogeneities involved. Okay. So it has to involve all the non-homogeneities of the bulk material as well. So, and hence the word representative, that this has to be the representative of the bulk material. So what we are going to be doing, we are going to be, this matrix is going to be of a titanium alloy, material properties of which are already present in the ANSYS. And there's going to be a spherical inclusion of tungsten carbide, which is going to simulate, and this combination of the two is going to simulate, as I said, a fictitious metal matrix composite. And we are interested in seeing what is the uniaxial tension behavior of this particular composite. So for this particular composite, I have picked up some kind of, again, as I said, that it is a fictitious material. I have picked up a fictitious kind of geometry parameters as well. One of the most important thing, I don't know whether any of you has come across this thing, but whenever you are doing a particle kind composites, you have to know the size of the particles in the matrix space. So this is where I'm starting. I have picked up a particle size of 2 millimeters, which is pretty large as compared to many metal matrix composite. But since it is a fictitious one, I can pick whatever I want to. I'm picking up this F is the volume fraction. So this is basically the fraction between the volume of this inclusion and the volume of this whole cube. So I have picked up a 10% volume fraction of the inclusion. So this particular thing in the numerator is the volume of a sphere, and then the denominator is the volume of the whole cube. So I have picked up 0.1, and after substituting the value of R and 0.1, I can estimate the value of the side of the cube. So it is coming out to be around 3.5 millimeters. So R cube is going to be 3.5 by 3.5 by 3.5 millimeters. And the displacement I'm going to be applying on this edge, the total displacement should be around 0.4 millimeters. So if you recall, and if you have once ever done the tensile test, you know that most of the tensile tests are the displacement control test. So we control how much displacement we are going to be applying. So the same is going to be happening here as well. So this is our problem statement. And again, as I said, that we are going to be applying a uniaxial tension here. So we'll be interested in this stress strain response. Moving forward. So the pre-analysis thing, if you recall, we have very horrible and very scary kind of equations in the pre-analysis of the last part of the last session. But if you compare today's things with the previous one, they were like, I don't know, very, very, very small and very simple. They'll start to look very simple in front of these things, because the problem which we are tackling is a classical Eshelby's inclusion problem. Sort of, not an actual one, because in the Eshelby's inclusion problem, your inclusion can undergo plastic deformation as well. But in our case, I'll restrict my inclusion to elastic deformation only. So a new thing which we are going to be studying today is to see how the plastic behavior can be simulated, or the nonlinear material behavior can be simulated, inelastic material behavior can be simulated in ANSYS. Because for a lot of us material scientists, we need to keep the plastic part in view as well. So just for the sake of an idea, you can see I have given the link to one of the lectures from Stanford about this particular problem, Eshelby's inclusion problem. So this is probably the guy. He was pretty genius to work on this thing back in the days. So start to look at these things. I don't know whether you can, yeah. So I doubt the things which we encountered in the last one were any difficult if you compare them to this one. And imagine you have to do all these things by hand. So analytical results exist for this problem as well. It's not like the case we were discussing the last time where the analytical results were only for the infinite plate, but in this case, the actual results exist. But I don't know whether anyone of us has the courage enough to actually tackle that. So what the Eshelby inclusion problem does, so or what is actually the problem, or like the aim of today's thing or exercise. The aim of today's exercise is to see that when we join together two dissimilar materials, So how the response of the composite is going to be, how different it is going to be from a pure material. So for a pure material, it is very simple. But what if I start combining two dissimilar materials or create some kind of inhomogeneity to see what is going to be the response of the, or the homogenized response of the two? Okay, so this is basically today's exercise. So we know, or we will know, the response of titanium alloy. So in the stress strain graph, the titanium alloy response is in orange color. Okay, the stress strain response of tungsten carbide is plotted as this gray color, and you can see that it is way more stiffer than the titanium alloy. Okay, and I don't even try to go into the plastic part of tungsten carbide, okay, because it's I don't know what's the strength of it. So of course, as I said, that you can compute the response of the composite of the two using this analytical result, but it's going to be too complex. So I haven't even tried to calculate this thing. But another way in which a lot of guys who work on the soft emitter, things like elastomers and stuff like that, and CFRPs and carbon fiber reinforced things, GFRPs, glass fiber reinforced plastics, these guys are concerned with this part, the elastic region, and with a very good approximations, without losing a lot of accuracy, they can do the homogenized, or they can find the homogenized response of a composite material using this result or this simple calculation as well, where you can just do the volume fraction, like use the volume fractions here. E is the stiffnesses or Young modulus of the two phases 1 and 2. And this small V1 and V2 are the volume fractions of each of the two phases in present. So like phase, whenever I use phase, it means that each of the physically different material. So titanium alloy is going to be one phase. It has its unique physical and chemical composition and properties. And tungsten carbide inclusion is going to be another phase. Okay, so that phase has its unique physical and chemical properties as well. And this thing is called the inclusion, and the titanium alloy is going to be called the matrix. Okay, so whenever I say a matrix, it should mean that I'm talking about the titanium alloy part, and inclusion is going to be the tungsten carbide sphere. So these are the Young modulus of each of the two phases, and these are the volume fractions of each of the two phases. If you use this result or this formulation, you can calculate the value of the homogenized Young modulus to some extent, to some accuracy. But what I've done, just for the sake of comparison, I have plotted the homogenized value here as well of the titanium alloy and the tungsten carbide. I should have cut it here. I don't know why I have plotted it beyond this thing, because I can not possibly see how much it's going to, or how it is going to behave in the plastic, where the titanium part has gone into the plastic region. So just consider it to end up somewhere here. So you can see that. And this blue line is actually the result from the FEA, which we'll be doing today. You can see that there's a huge deviation from it. Why this huge deviation is happening, I'm going to try to explain some of these things while we go through it. But you can see that for this particular problem, where we are dealing with one of the material which can undergo plastic deformation, and pretty ductile in it. So we cannot actually use this homogenization technique, a simple homogenization technique, to calculate the response of this composite. And hence, this gives us the motivation for actually doing this FE analysis. So any questions up till now? Because I want everyone to have a very clear understanding of what is going to be happening here. so many material scientists and still I have no questions, because I think that I'm bound to make a mistake, which is going to be a very obvious mistake for a material scientist, but for me, like a mechanical engineer, I may have overlooked that. Okay. Will this require modeling the interface? There will be an interface for sure, definitely, because we have two dissimilar materials. We will be modeling that interface, definitely. But the behavior of that interface, we will be taking a very huge, very blunt kind of approximation. We'll assume that they are gonna stick to each other no matter what. No matter what happens, they'll keep on sticking to each other. So this is some kind of approximation which we are gonna do. It may not be the case in the real case scenario, but it is going to be a good approximation, good enough approximation. Anything else? You can raise your hand, I can unmute you. That way it's going to be faster. You don't have to type a lot of things. Will we account for grain orientation? The material properties which we'll be using are going to be isotropic in nature. We are not taking care of the any kind of an isotropy, either in the elastic part or the plastic part. So we don't have to worry about the orientation and stuff. No. Because grain orientation start to be important only in the case where we have anisotropic properties, but I won't be using those kind of properties. And then again, if you see the scales I'm using, they are definitely way higher than any grain sizes or any practical grain size application we have in real case scenario. I hope I was able to answer your question. Okay, can ANSYS? Yeah, definitely it can. ANSYS has no limitations. ANSYS or any other FEA software has no limitations. The limitation is only on what people have already developed. So like if people has already come up with a numerical modeling of any particular phenomena, you can definitely go and program that phenomena in any of these FEA softwares. So FEA softwares are basically FEA solvers. So if you recall, if I go back here, so there is a step called physics step. So this is the step where you need to be careful what kind of material behavior you are interested in. So for example, as Hamza asked me a bit earlier, that what about the grain orientations? So in today's problem, grain orientation is not going to be a problem or a concern for us because we are at a very much higher scale. But for example, if you were looking at these things at micrometer scale, so there the grain orientation starts to play a very important role, okay? So if I start to play around with isotropic properties at that scale, I am doing a huge mistake, okay? So what I need to do at that scale, I have to be pretty cautious about what are the anisotropic elastic as well as anisotropic plastic properties. What is the slip behavior in the titanium alloy? Is there something like the conditions are allowing the twinning to happen? How is the behavior at the grain interfaces? So all these things become a very important aspect, okay? So for that thing, I won't be using the physics which is already built into it right now, or the physics which we are going to be using today. Rather, I'll be using something called crystal plasticity, FEA. So there's a thing called CPFEM, which is crystal plasticity finite element method, on which I worked while I was doing my PhD. So at that scale, we make use of that thing. If you go even a smaller scale, you start using something called discrete dislocation dynamics thing. If you go even smaller, you guys are already taking the courses or the session with Dr. Demkovich on LAMPS, which is molecular dynamics. So you need to take help from them as well. So it's all about scales, that at which scale we are working at. So ANSYS can definitely make use of the anisotropic behavior as well. But with the current built-in things, we cannot. All right, so any other questions before we start moving on to this thing? All right, cool. So let's start. So the startup is exactly the same as we did last time. I guess most of you are already familiar with the interface and everything. What we are going to be doing, we will, of course, we have to have an HPRC and the VPN installed on our things. We will start by going to this address, which is portal.hprc.tamu.edu. We'll be using ADA again today. So I click there. It is going to ask me about my net ID and password. All right, so I'll go to interactive apps and I'm going to select ANSYS Workbench. I'm going a bit faster on these things because I assume that everybody already are familiar with all these things. So again, the version we are going to be using is the latest one available on HPRC. Number of hours, let's keep it for 4 for now. If you disconnect before it, you won't lose the rest of the hours. Okay. Number of cores, 1 is fine. I ran these calculations yesterday on 1 core. It's perfectly fine. But when you will be doing a refined analysis on this problem, if you refine the mesh size I'm going to use, number of core 1 is perfectly fine for that. And the memory 2 GB is perfectly fine for that problem. But if you try, and you will try, I urge you to try the same problem with more refined mesh, then I recommend you to go to 2 cores and probably 8 GBs, okay, of memory. Once you do that thing, you may not get the session right away the way you get it at these resources, because you will be put in a queue, and whenever these resources will be available, you will be allowed to have this session. But it's worth, the wait is definitely worth doing. So you have to, like, otherwise what's going to happen, if it is going to pull us a lot of memory out of the thing system, it may crash. Okay, so for now, keep it to 1 core and 2 GBs. Node type GPU is already pre-selected because that's the only option for running ANSYS application. Click on launch. Lisa, can we do it? Can we go to 2 cores and up to 8 GB memory on the GPUs?
You can increase the number. I'm sorry, did you say what?
Can we increase the number of cores and the memory both?
Yes,
and
with
run
the
it on
number of
HPRC?
users that we have, absolutely.
Cool. All right, so yeah, okay, so as I was telling you that you can share where you what you are working on and where you are stuck. You can right click on this thing and copy the link address and share that link with me in the private chat if you need any help doing a particular step, okay, during the today's session. So let's click on launch NoVNC to start doing that. Okay, let me close these things. Okay, so again, this is the Workbench environment. If you are not already, click on the maximize thing to maximize it so that you see the whole interface. Let me close my video. The internet is fine now. It's not giving me anything, so I'm leaving my video on. Okay, so again, the problem which we are tackling today is going to be in a static structural case. We don't have any dynamic events happening in our analysis. We assume that we load the specimen in a quasi-static way so that we can make use of the static structural thing. So again, what I'm doing, I am I have clicked on the static structural here and now dragging this thing to this box to create a static structural environment. So now this is the static structural environment. If you recall, let's go back and see what else we need to take care of. So we have done that. We have launched it. No VNC. ANSYS Workbench is open now. We'll be saving our things as ANSYS secretarial under our Scratch directory. I hope that you already are conversant with the Scratch directories and everything. Yeah, try not to close this window. If you close this window without saving your work, all the progress will be lost. So make sure that you don't close this workbench window because it will close your session then. But if you by mistake have closed your tab, you can reopen it by clicking this button here. So in that case, your progress will not be lost. So one way of going forward is to keep on saving after each step. Try keep on saving it. Okay, so the startup is that the workbench is started now. What we need to do, we need to maximize this thing. We have added the static structural thing. Make sure that the units are consistent again today. So I told you that last time as well, that you have to keep making sure that the units are consistent for each of the environments which we'll be dealing with. We'll be dealing with three environments. One of them is going to be the workbench, the other one is going to be design modeler, and the third one is going to be mechanical. So make sure that whenever each of these three environments comes up, you select the consistent units. So we'll be working in millimeters today. So I'm using this thing or selecting this term here, which is metric millimeters. Okay, so I've clicked that. After that, we need to select or import these two materials. So if you recall in our problem statement that we are going to be working with titanium alloy. NL is for nonlinear. So we are interested in the nonlinear property of the titanium, which is the inelastic property of the material, which is the plastic part of titanium. Okay. So we'll be interested in that today. So we'll use pick up a titanium nonlinear material properties from the material library already built in to ANSYS, and we need to pick up tungsten carbide. So we need to import these two things today. Okay, so I'm having a failed to connect server on no VNC error. Do I need to wait and try that? Failed to connect to server. I guess your session is over already. That's why you are getting this error.
Are you refreshing the page or did you relaunch? Okay, yes. If you relaunched and you get no VNC error, then you'll have to respawn one. So go ahead and delete it and make a new one.
All right, since we have so few of us today, let's wait for Christopher. Christopher, we are waiting for you. As soon as you are ready, tell me. Okay, so we will be selecting these two materials or picking up these two materials from the library. Of course, you can add your own materials the way you did last time as well. Like you just click here and start putting in cool. So you can definitely start adding up different properties to your material, whatever material properties you are interested in. So some of the material properties, okay, let me try. We did it last time as well, but just for the sake of refreshing it or reviewing it. So I just added a fictitious material called agenium. Okay, so for agenium, you can add these physical properties, and they may or may not be important for any particular analysis you will be running. Okay, you can put in isotropic elasticity, which is good enough approximation for most of the macro scale analysis. You can put orthotropic elasticity as well, which you may be interested in when you are dealing with composites or woods, and the cases of cases like that. You may want to have an anisotropic elasticity if you are working at the crystal or the grain scale. Okay. So you have all these options built into ANSYS already. You can have hyperelastic experimental data like uni-axial test data, bi-axial test data, shear test data. So if you have like stress strain data already with you, you can just put in those tabular values of let me add bi-axial test data. So what it is asking for? So it is asking for a tabular value, and the input you are going to provide is this. So if your data is temperature dependent, you start giving the value of temperature and the value of stress and corresponding strain and stress for that particular temperature, and populate this table from your experimental results. Okay, and that your analysis will have the material response of the material you have actually measured in the lab. Okay, so you can do that. So let me delete it. I'm not interested in right now. You can add shear test data, volumetric test data, and a lot many other things. Okay, if you have like all these things, you can make use of hyperelastic experimental data. There are some hyperelastic models which are built into it as well. Some of them like Moni-Rivlin and stuff like that. The people who work on soft matter are more familiar with these things. So you can make use of these things as well. Okay. Then Chabochi test data you can put into as well. Plasticity can be introduced in multiple way. The kind of plasticity we'll be making use of is bilinear isotropic hardening for today's case. In that one, you need very minimal amount of inputs. You need to put in the Young modulus, you need to put in the Poisson's ratio for the elastic part, and for the plastic part, you need to provide the value of yield strength and the tangent moduli. So these are, so like bilinear isotropic hardening is one of the most simplistic kind of hardening a material can have, or plasticity response a material can have. You can have multilinear isotropic, you can have kinematic hardenings as well. What it is, this is not a material science session, so I'm not explaining all these things. But what I'm trying to do here is that you can pretty much make use of the built-in models for most of the problems which you will be facing. You can put in the creep things are built into it as well. The fatigue life and all these analyses are already built into it as well. The strength things, like if you are interested in when the material is gonna lose its load bearing capacities and stuff, you can do those kind of analyses there as well. Gasket analysis, gaskets are dealt a bit differently. Their responses are a bit different, so gasket models are built into it as well. Viscoelastic, shape memory alloys. I think shape memory things are going to be pretty simplistic. Yes, we'll be using these. That's why I'm taking you through all of these things. Damaged cohesive zones. So somebody was asking me about the interfaces. So if you want to have some kind of realistic interface, you may want to explicitly include cohesive zones as well in your exercise. We will not be doing it today. If you are dealing with the failure, so what are the fracture criteria, crack growth laws and stuff like that. So all these things, or all these physical phenomena are already built into the system. What is not, the thing I was talking about earlier, crystal plasticity is not there because it is a kind of complex kind of model. So it's not built into it. But of course, you can create your own models, and how to do that is beyond the scope of today's thing. All right, so this is the way you can add your own material properties into it. Why I am taking you through all these things is because in the exercise, I'm going to ask you to add your own material and run the same thing with your own material properties. Okay, so that's why I'm taking you through all these things, or telling you how to do these, adding your own material thing. All right, so let me delete this thing. We are not adding any material today. What we'll be doing, we'll be taking care or making use of this engineering data sources. Okay, So for that, just click on engineering data sources, and a couple of resources or this sources will come up here. So if you read, so the first area has the heading engineering data sources. So you first pick up one of these source, then the materials which are present under each of these are gonna be listed under outline of favorites. And if you click on each of these materials, the properties already built into it, or the physics already built into it, will appear here as a properties of outline. Okay. So let's start. Let's add the titanium alloy first. So for that, since I told you that we'll be interested in the nonlinear responses or the inelastic properties of it, so I'll go to general nonlinear materials. So if I click general nonlinear materials, all the materials present in this are going to be listed under these general nonlinear materials heading. If I keep on going down, I'll find this material here, titanium alloy. If I click on this, you can see that the properties are already built into it. The value of Young moduli is there. The Poisson's ratio is there as well. The nonlinearity is included using the bilinear isotropic hardening thing. The yield strength is already given here, and the tangent moduli is given here as well. So if you click on one of these things, you can see the stress strain response, which is already built into it. So this is the stress strain response which is built into it. Okay. So to add this material for today's exercise, what you need to do, you need to click on this small plus sign beside it. So if you click on this, so this is important to include it in your current analysis, because right now it is only present in the engineering data library. So in order to import it to your analysis, you have to click on this small add to engineering thing. So once that is added, now I'll add the other phase, which was tungsten carbide. So for that, I will go to the resource here at the top, which is Granta Design Sample Materials. So I click on that. All right, so now again, if I, come on. Okay, so all the materials present under this heading is listed here: copper, cast, galvanized steel, granite, high strength alloy steel. A lot of interesting things are there: nylons, phenolic foams, plywood, polyethylene, and stuff like that. If you are interested in the composites, I guess there is another library for composite materials as well. If you are interested in geomechanical properties, there are some geomechanical stuff there as well. So a lot of stuff is already, commonly used material stuff is already there. So I look for tungsten carbide, where it is. Here it comes, tungsten carbide. So if I click on this one, let's see what are the properties already, not this, tungsten carbide. Yeah. So in the case of tungsten carbide, only the elastic properties, isotropic elastic properties are there, and their tensile yield strength is there, and tensile ultimate strength there as well. Okay. So I was wrong when I said that only the elastic properties are there. But again, we will not be reaching these things. We will not reach to this point to be able to make use of these things. All right. So again, in order to add this, I'll just click on this small plus sign beside it to add it to our analysis. Okay. So the question was, is there a search feature for the material database? Good question. I was looking for it yesterday, but I couldn't find it. But good luck. Try in your own time, see whether you can search for it. It should have one, but I couldn't find one. So yeah, try and find it for yourself in your own time. All right, once that's taken care of, just click on this engineering data source once again to switch it off, and you will see that these two materials are added to your engineering data now. Okay, so what I'll do, I'll click on this suppress checkbox for structural steel, because we'll not be using this thing, and it was there by default when we started ANSYS workbench. So since I won't be using it in our today's analysis, so I'll just suppress this thing. Make sure that both of the materials you are going to be using are listed under this heading. Once that part is taken care of, let's close it and go back. Let's see what's the next step. So we have imported these two materials. We have imported titanium NL and tungsten carbide. Everybody is with me up till now. I guess we haven't done any complex things so far. The complex thing is going to start now. Anybody is stuck anywhere? Cool. So now for the next part, we're going to start to create the geometry. Keep in mind that we need to create a 3D cube. Sides, the length of the sides of which is going to be 3.5 millimeter each. And we need to have a 2 millimeter diameter sphere in the center of it, exactly in the center. Okay. A new thing which we are going to be doing today is, since the material properties are isotropic, the behavior is going to be isotropic as well, both for the inclusion and the matrix phase. And what is the other thing? Yeah, so the geometry is pretty much, the geometry has symmetry as well. The material has isotropy in it. So we can make use of the symmetry conditions present in our problem, and we'll make use of it. Why we are doing it today from the very start is that if we create the whole model, it is gonna be very heavy in the sense that it is gonna take a lot of resources, computation resources. Okay, so we don't want that. So that's why we'll make use of whatever symmetries we already have in our system. Okay, so let's start. If we wanted to create our own models outside of ANSYS using other software, can we import these models for analysis? Yes, you can, but don't ask me how to. I know that at the back end of ANSYS mechanical these days, mechanical APDL is still present. There used to be a thing called mechanical APDL back in the days before ANSYS was not this fancy. Probably I'm talking about 2012, 2013. So APDL is still present. You can, and the user defined, it is called user defined functions in APDL, UDF. And you need to program your material behavior in C++, I guess. Okay, and then you'll have to import it. How to do that in Workbench environment, I'm not very sure, but I am definitely sure I have seen people doing it in mechanical APDL. You can find, if the ANSYS is installed in your machine, mechanical APDL is there as well. It automatically installs as well. So if you just type in the search bar mechanical APDL, you'll find it. But then again, to start mechanical APDL, you don't have it here. By default, what you need to do, you have to start a VNC environment first, and then I don't know whether you are in the Dr. Damkovich class. Are you in Dr. Damkovich class as well? Joshua, I'm asking you. Joshua, yeah, Joshua. I'm asking you. I hope that I'm pronouncing your name right. Are you in Dr. Damkovich class? Dr. Damkovich, Michael Damkovich, Lamp's class. Oh, you're not. Okay. Then I'll ask you to go through the HPRC, what it's called, help manual. Lisa, where's the resource about the softwares and how to use them?
The wiki, correct.
Yeah. So can you please share that resource address with him so that he knows how to start mechanical APDL? If the environment I'm talking about is mechanical APDL, let me write it in the chat as well. Mechanical APDL. Oh. All right, my keyboard has given up on me. Just give me a second. Let me switch the batteries. It won't take long. I knew that it was going to happen, but I was waiting for it to die completely. All right, sorry. What is it? Mechanical APDL. This is the name you are looking for. So run the mechanical APDL or go through the resources of mechanical APDL and you'll find out how to add your own material behavior or how to code it even. You will find some examples there. All right, let's start geometry. Again, I'll ask those guys who are using ANSYS on their own machines to right click on it and use new geometry using design modeler. We'll be again using design modeler, not the space claim thing. For rest of us who are using it on HPRC, just simply double click on geometry to pull up the design modeler. Be patient, it takes some time and it shows the progress of design modeler here at the bottom. Once we have the model or the geometry, we'll take a break. We'll take a small break. I hope we don't exceed 15-minute mark. We should be able to create the geometry in 15 minutes. Let's see. Okay, so this is the environment you're already familiar with. Again, I'll ask you to maximize the thing and make sure the units are set in millimeters. Make sure that the millimeters are selected from the very beginning. Otherwise, what's the worst that can happen? Yeah, your model is gonna be off scale and everything is going to be very small and everything. So let's select the correct units from the very beginning. So I'm going to be modeling in the millimeter thing. So let's select it from the very beginning. Again, anything starts from sketch. As I told you last time, three-dimensional bodies start with 2D drawings as well. So there are two very important operations whenever you come across any kind of 3D software or 3D modeling software. There are two features. One is called extrude. The other feature is revolve. So you can think of extrude as a die. So like if you are doing extrusion, what you have a two-dimensional die and you push material through that die or you pull material through that die. So extrude is going to do exactly the same thing. For extruding anything, you need to have the cross-section shape of whatever shape you want to extrude. Okay. So if you're creating a three-dimensional, for example, a cube, you start with a square and then pull the square in the third direction to create a cube. Okay. So this is a very important feature, extrusion feature, which you will come across on any 3D modeling software. Extrusion works both ways. It can add material to your geometry and it can remove material from your geometry. Okay. So for example, you want to create a cube and then you want to make, for example, a hole in that cube. So what you will do, you will add the material by creating a rectangle and then pulling it in the third direction first. And if you want to remove the material, you will create the cross section of the shape you want to remove first and then remove the material in the third direction as well. So extrusion works both ways. You can remove the material as well as add the material. Then there is another command called revolve. So it may have different names. Sometimes people call it revolve protrusion, but there are several other names for this feature as well, for the revolve. So I asked the people, so the best way of visualizing the revolve feature is a potter's wheel. A potter's wheel. So what a potter do, he has a wheel which is rotating at a high speed, or not specifically high speed, it can be low speeds as well. He puts some kind of clay on top of it and then start to shape it while the wheel keep on rotating. So the revolve feature does exactly the same thing. So you what you need to provide for the revolve feature is to give some kind of cross section, axisymmetric cross section of the thing, and then revolve it around a defined axis. So again, revolve feature works both ways. It can add material, it can remove material as well. So for our geometry today, how we are going to create this geometry, where it is. Yeah. So what we are going to do first, we are going to create this square and then extrude it in the third direction. So this is the extrusion which we'll do. Then we'll create a cross section like a hemisphere, not hemisphere, semicircle. We'll create a semicircle and then rotate that semicircle about a fixed axis to create the sphere. Okay. So this is what this is how we are going to do or create the geometry which is required for today's session. Let's go back. So I said that we'll create the cube first. So for that, again, as I said, that you need to start with some kind of sketch or a drawing. I'm going to create a sketch first. So since I'm going to be creating it on the XY plane, let's click XY plane first. So it appears. Then click on new sketch. So what is going to happen in the tree outline, you'll see that a sketch called sketch 1 will be added under XY plane. Okay. You can rename it, give some meaningful name. It may not make sense to name each and everything here because we have so little amount of features. But if you have a lot of features, I urge you to give meaningful names to each of these things. Okay. So let's call it cube. Okay. To work on this sketch, you need to go into the sketching environment. Right now you're in the modeling environment. So in order to go to the, or how to go to the sketching environment, while the cube is selected, click on this sketching tab on this side. So once you click it, all these sketching options will appear in the toolbox. Okay. So as I told you that we'll create a rectangle or a square first and then extrude it. So let's select this option called rectangle for, and again, as I told you that these small red points signifies that what are the points where you need to click. So it is telling me that you first have to click to create one corner of the rectangle, then click, then drag it to a certain size and then click on the other corner. So I'm going to click this. Since we are creating it on the XY plane, let's see the planar view of it, how to change the planar view. Click on this triad on the corner. Since I want to have a view perpendicular to the Z axis, so let's click on the Z axis and I'll get a planar view. Okay. Now click anywhere to put the first point and then drag it and click anywhere else. So now you have created a rectangle, a rough rectangle. The dimensions of which we are not concerned about just about now, but in a little while we'll dimension it. It is a good practice to keep the origin. So this is the origin where all the X, Y, and Z axes are intersecting. It is a good practice to have your model centered at the origin. It is a good modeling practice. I repeat, it is a good modeling practice to have your body center, the center of the body coincide with the origin. Okay, it gives a lot many it helps you a lot in the longer run. Okay, after creating this rectangle, let's dimension it and dimension it according to the dimensions which we are already given, 3.5 by 3.5. And as I said that I will constrain it to be on the center of this square to be coincident with the origin. So for doing that, I'll make use of dimensions. Okay, so there's a thing called general. So what general does, if I have the general selected and I click on this line, what it is going to do, it is going to give me the length of this line, okay, or the edge. If I have an arc drawn here and if I click on that arc with while general selected, the radius will be added to my system. Okay, so general is a general tool for adding any dimension. So only the most important dimension of any feature will be added while you are at it. Of course, you can select horizontal to put a distance between these two lines and vertical to put a distance between these two lines. You can use it that way as well. All right, so I'll add the length of this side and I'll add the length of this side. In addition to these two things, I'm also concerned with the position of this box. Since I've already told you, I want the center of this box to be at the origin. So for that, excuse me, for that, I'm going to add some more dimensions. One of these is going to be horizontal distance between this axis. So I'll click on this axis first and then this edge. So it is going to add the distance between these two lines, the horizontal distance between these two lines. Next, I'm going to add another dimension, which is going to be the distance between this horizontal axis and this top face. Added. So now I have dimensions H1, V2, H3, and V4. All of these should be appearing here at this corner. Okay, so I'll update it accordingly. H1 is supposed to be 3.5. V2 is supposed to be 3.5 as well. The distance between the center and this corner should be half of 3.5, which is 1.75. If I'm not wrong, I guess it is, yeah. And the distance from this top edge to this should be half of it as well. So 1.75. So if I zoom in, and how to zoom in, click on anywhere here in the graphics window. And if you scroll the mouse up, it will zoom in. And if you scroll it down, it zoom out. So if you zoom in, you can see that we have a square now. And the center of the square, which is represented by this small, I don't know whether you are able to see it or not. There's a small square centered at the origin as well. So this small square is signifying that this is the center of this square. Okay. Once we have created the cube, what I'm going to do, I'm going to extrude it. So in order to extrude it, I have to come out from this sketching mode. So I'll go back to the modeling mode by clicking on this thing here. If you want to have an isometric view of things, you can click on this small sphere on the triad. If you click it, it's gonna show you the isotropic view. Again, you can zoom in and zoom out by the mouse scroll. If you want to pan this thing, you need to press Control key and press the center mouse button, middle mouse button, or the scroller you have, and you can pan the whole geometry. Okay. If you want to have another rotated view, you need to press Control key and if you want to rotate it, then you have to press your mouse button without pressing the Control key, and it will rotate it. Okay. So these are some of the operations: zoom in, zoom out, panning, and rotation. So make sure you know how to do all these things, because when you are doing the 3D, you have to like rotate it a lot to actually see it from different sides or different angles. Okay, so I told you that we'll first extrude a cube. We have created the die of the extrusion. So let's think of this sketch as the die. Now we want to extrude it. Okay, so for doing that, I need to make use of the feature called extrude. You can find it in the ribbon bar at the top. If you click it, an extrusion will be added to your tree outline. The details are already here, and it is asked, the first input it is asking you is for the geometry. It is asking you for what is the die for this extrusion, or what is the geometry which you want to extrude. So, but since you already have one geometry present, or you only have one sketch, it has taken it as it has picked it up as default. But you need to confirm it. If it was not selected by default, you have to click it either here, or you can click or select them individually in the graphics window. Okay. Once you have selected or pointed out your die, this is your die. Now you want to tell it what to do. So there are different options here. You can see that you can add material. You can do another thing called add frozen. But if you already, so right now it is not giving you the material removal of the material thing because you don't have any material present right now. But if you have some material already present, it will give you the option of removing the material as well. Okay, but right now it is only giving you the material, the option for adding the material. And there is another thing called add frozen. What it is, I'm not 100% sure because I'm not a user of ANSYS, but for now we can neglect it. Keep it to add material for now. Yeah, so the next thing is we need to tell ANSYS how far you need to pull it. So since it is a cube, the third dimension should be 3.5 as well. Okay, there's another thing which is called in which direction you want to pull it. You want to pull it in this direction, or you want to push it in that direction, or you want to pull it equally in both the directions. You can select this here. Okay, so it is called direction. So if you click on this small arrow, there are different options appearing here. So the normal is coming out of this, reversed it going in, and there is another option called both symmetric. So it will add this much amount of material on both sides, and you can have both asymmetric, in which you have a different length added on this side and different length added on the other side. So right now I want to add symmetric on both sides, and I want half of it on this side and half on this side. Why I'm doing that? I just told you that it is a good practice to keep your model's center coincident with the origin of the whole thing. So that's why I'm gonna add symmetric on both sides, and 1.75 millimeters will be added on each of the two sides. Once you have selected this thing, you can see that now your cube is taking shape. This blurred out edges is basically telling you what are going to be your final result. It has not created yet. If you recall, I told you that if ever there is a bold sign in ANSYS, it means that you have to take some action here. So click on this and click generate to generate this box. So now you can see that it has added the material. So the material is in the gray color here. So whenever you have some material, it will be shown in the gray color. Now you can rotate it and see it from different angles. You have created your 3D geometry now. Cool. Now let's move on and create the sphere in the center. I hope we won't take too long for that. Again, if you recall, I told you that if you want to create something spherical or cylindrical, you need to make use of the feature called revolve. Okay, so again, it is like a potter's wheel. For this revolve operation to take place, I need to give some kind of a sketch or the shape in which we want to rotate this thing. So the shape which we want to rotate, I told you, is going to be a semicircle. So let's create a semicircle sketch. Again, I'm going to be creating this sketch on the XY plane. I have clicked on XY plane. Create a new sketch. Let's call it sphere, or better inclusion. Okay. Again, in order to create this sketch, you need to go into the sketching mode. I'm going a bit faster now because now I assume that everybody of us are pretty much conversant with the environment. So I click on Z axis here to see a planar view. Again, I'm going to create a semicircle in the middle. So there are different options for creating arcs. So anything which is not a complete circle is called an arc in most of the CAD packages. So there are different type of arcs present here. You can create an arc. You can see that you can create it by 3 points by giving 3 points on the arc. Or you can do it by selecting the center and then 2 corners. So I'll use arc by center because I know where the center of the arc is supposed to be. So I'm going to click on arc by center. Okay. If you hover over this center point, I don't know, it is not showing today when I'm using it over Zoom, But if you are doing it on your own, and when I was doing it on my own yesterday, I can see small p appearing. Okay, see, a small p appeared. So there's a small p means that we are over the origin. Okay. Similarly, if I go over this point, if I hover over this small point and wait for it, a small p appears again. It shows that we are exactly at that point. So I want to add the center of this arc at the origin. So I'll wait for this p to appear before clicking on it. Okay, so let's see. Okay, I assume that I have picked the right point. Once you have clicked the first point, now I want to add the second point on this axis, on this corner, and then keep continuing up till this corner. So it created a semicircle, and its center is at the origin. And one more thing is that both of these points are on my vertical axis. I'll close this geometry by adding a line. Again, you can add a straight line by clicking first on one corner and clicking again on the second corner. So now it has added a line. So it is creating a small d here, not a small, rather large d here. Okay. So once you have created this geometry, now I know that this is the thing which is going to be rotated about the vertical axis to create the sphere. Okay. So, okay, one thing I was forgetting is the dimensioning. So let's dimension this first. As I told you, if I click on general, and now this time if I click on this arc, it will add a radius. So since the diameter was 2 millimeters, radius is going to be 1 millimeter. So let's add this 1 millimeter thing. Ideally speaking, the length should be already updated according to this radius. Okay, but one thing to be sure of is to see whether the center is located at the origin or not. To check that, just add a vertical or dimension and add this dimension from this center axis and this corner. So it is giving you that your system is going to be over constrained, which means that this thing is already present on the center. Okay, I'll say it again. There was an error which was when I added a vertical dimension or distance from this axis to this, it gave me an error saying that you are over constraining the model. This means that since you have already defined this circle's center to be at this center, you don't have to explicitly define the distance as well, because it is understood that if this is the radius of the circle, that whatever the distance between these 2 points is going to be. All right, so once you have done that, let's go back to the modeling environment. Okay, now we're in the modeling environment. Let's have a look at the isometric view. Now, as I told you that we want it to rotate, and we will be using the revolve feature to do that. So click on revolve. So it will add a revolve feature here. Now, these are the inputs which you need to provide. If you recall, I told you that everything in the yellow color has to be provided. Okay. So for the geometry is already selected. It has automatically selected this inclusion geometry. Okay. If it has not, you can manually select these 2 lines while pressing Control key. Click on apply to confirm the selection. Now the next thing is it is asking you for the axis about which you want to rotate this geometry. So click here first so that it knows that this is the information you are providing to it. Then go and select this line, this vertical line. So axis of rotation is the line about which it will rotate this geometry. Okay. Once you have selected this, in certain cases, you need to provide either you are going to rotate it clockwise or counterclockwise. So you can switch between the 2 by clicking here. For us, since we are giving it the complete 360-degree rotation, it is not important which direction it's going to rotate. Okay. Once you have selected that, click on apply. Now recall I told you that you can add material, you can remove material, many other things. So this is the option here. Now, if you click on the drop down menu, now we have a lot many other options as well. Since we have already added material, we can remove the material as well now. Okay. So the options are, we can add material. If we add the material, any wild guess what's going to happen if I just add the material? If I click on the option of add material and generate it. Any guesses? You can raise your hand so that I will unmute you rather than typing it. Okay, nothing is going to happen. Yeah, it can say that, it may not. I think it's not going to tell it, say that it has the material already there. It will just add the material and it's not going to make any difference. So you are adding material within the material. So nothing is going to happen. It just merges the material existing. No, it's not going to merge. So it will add material where the material was already present. So nothing's going to happen. Okay. So we don't want to do that. It will not distinguish between two different bodies. If two different bodies are present at the same point, it is going to consider it as a single body. Okay. So we definitely don't want to add material here. What are the other options I have? If I click on cut material, think of it as it is going to remove the material, whatever the material it will encounter within this D region and about this axis. So it's going to remove all that material. Do we want that? Or you can say that it's going to create a void in the middle of it. So do we want to have a void in the middle? Definitely not. We don't want a void in the middle. What we want it to slice the material. We want to think of this D circle or this D shape as a wire cutter. Okay. And I want that wire cutter to rotate about its axis to create a boundary between two different regions. So it will divide this whole single block of material into two different regions. One of them is going to be spherical region in the middle, and the other region is going to be the region around it. So let's select slice material option. And again, since we have already provided here, if I want it to go only halfway or like quarter of the way, I'll click or change this much amount of angle. So right now 360 means it is going to go all about, all around it. Okay. As thin surface, it is not important right now. Target bodies. If you have multiple bodies here, and if you want to cut only part of the you want to have this feature applicable only part on only part of those bodies, you can make use of this thing as well. Merge topologies. So imagine that once the wire has gone through, we will have two new surfaces created. One of the surfaces is going to be the outside surface of the sphere, and the other surface is going to be the inside or like the surface of the cube, which is in contact with the sphere. So it is asking you, do you want the topology to be merged together? Since we are assuming that these two phases are going to be in contact with each other, we will keep this merge topology as yes. Okay, we want them to be merged together automatically. Okay, so there will be a distinction. There will be a boundary between the two materials, which will distinguish where one of the phases start and where the other ends, but they will be connected together. So this is what merge means. All right, let's generate it. And now, since you have some features within each other, it is gonna make the outer feature go transparent so that you can see whatever is happening in the middle. Voila, our geometry is completed. But one step is still left. We still need to, if you recall, I told you that since it is going to be pretty heavy on it, we want to apply symmetry condition. Okay, So let's quickly go through what symmetry conditions we can make use of. If we look at across YZ axis, we can see that there is a symmetry about X plane. Okay. If we look at it this way, we have a symmetry about Z plane as well. And if we look at from the top, there's a symmetry like this. There's a symmetry about Z plane as well. So we have symmetry about all the three planes. In terms of geometry, make sure that we have to be careful about selecting these symmetries, both in the sense of geometry as well as the physics of the material. So the geometry is symmetric for sure. Is the physics already is also symmetric about these axes? So the answer for our current problem is yes. Since we are using isotropic elasticity and we are using isotropic hardening as well, we are assuming that the mechanical properties are same in all the directions. We can make use of these symmetries. You will encounter certain cases. Just give me a second. You'll encounter some cases where you don't have symmetry in either the geometry or in the material case. Okay. As for example, I guess Hamza was the one who asked about the grains. So if you are talking about like if it is at a granular level, okay, it is assuming a titanium grain. Titanium has an HCl crystal structure and it is highly anisotropic. I strongly suggest you not to make use of the symmetry, okay, because it is not real. Although you will have a geometric symmetry, but not the material behavior is not symmetric. So I urge you not to use it in those kind of cases. Okay. All right. So we have material geometry have a symmetry, and the material is isotropic as well. All about we can make use of all these symmetries, and in order to make use of that, what I'm going to do, I'm going to only use 1/8 of this cube, because 1/8 of the cube is enough to be representative of my whole cube. Okay. So from the bulk material, we picked up a RVE, and even in RVE, we are only making use of a small block of it because of the symmetry. And why are we doing it? We are doing it to save on the computational resources, and the results are going to be faster. So in the tools, there's a thing called symmetry present here. So click on this and it will add a new thing, symmetry 1. What is it asking? It is asking you what is the symmetric plane, or where the symmetry is actually about. So I'm going to select one of these planes. Let's select XY plane first. Okay. And click on apply. So you can select things either in the tree outline or in the real or in this graphic window. Okay. So I clicked on XY plane and click on apply. It will apply the symmetry in the XY plane. Again, you can see that nothing has happened. Nothing has happened because the bold sign was there. So in order to get rid of it, click on generate, and it will cut off the half of the material. And now you will appreciate why I was saying that your whole geometry's center should be at the origin. Because if you don't have that, you'll have to create new planes to define the symmetries. Since your geometry is already on the origin, you don't have to explicitly define planes for creating the symmetries. Okay. Another symmetry, and this time it is going to be ZX plane. Generate. Another symmetry, this time about YZ plane. Generate. And now we are done with the geometry. Once you have came across up till this point, what you can do, just close this thing and make sure you save this. So let me call it QR inclusion RV. and save it. Once it is saved, now you are free to go for a break. Let's take a 10 minutes break because we still have a lot of things to do. Okay. So Lisa, we are taking a 10 minutes break. We'll be back around 11:55. All right, I'm back. Let's wait for another minute or two for the rest of the people to come back as well. I hope you're enjoying your tea or coffee as much as I'm doing, because I'm conducting these long lectures after a very long time. So I recall that before 2015, I used to conduct 3 back-to-back classes, each of 15 minutes long. And I prefer to go without using the mic or the sound system. So I used to deliver the lectures at the top of my voice in classes of 70, 80 students each. Oh, good old days. Not anymore. Not anymore. So even talking nonstop for 2 hours is taking its toll. One question, I guess I know one of the participant. I'm unmuting him. Advait, I guess you work on soft matter. So do you work on composites by any chance?
Right now, I haven't started yet.
Okay.
Yeah.
Cool. But your group is working on composites of any form?
Yes. So we will be doing some simulations on
composites. Okay.
Yeah.
So this particular exercise which we are doing today is going to be a lot, like hell of a beneficial for you. At least maybe we can, if we say that it's targeted at you, it's not going to be completely wrong.
Oh, yeah. So I'll be asking lots of doubts to you, of course.
Sure, no problem, no problem. All right, because like why I did that, or why I engaged you directly one-on-one, because I think you will be bringing in a lot of value. You'll be adding a lot of value to our today's session, because you are going to be the person who will ask me that, what about if we want this information as well? What about if we do this? So that we make this experience a lot more richer by taking some inputs from you. Okay?
Right. Yeah.
Okay. All right. Excuse me. Let's start again. I'm muting you again. Okay, where was I? I have to share my screen. Screen 2. I need to open the participants window. I need to open the chat. Where it is. I need to learn all these shortcuts now. Cool. So everything's set up. Okay. Now what I need to do, let's go back and see what's the next step. So we have created the geometry. We have created this much dimensions things. I have introduced the symmetries as well. Let's see what's the next step. The next step, we are supposed to create the mesh. This time around, we are not spending a lot of time on this. Reason being that meshing or a good enough mesh for this particular model is going to take a lot of time. Okay. And it is necessary to have a good enough mesh to get good enough results in this particular case. It is going to be very important. Okay. So, but then again, since we don't have time enough for that, and you will find enough number of tutorials and everything online for meshing these kind of geometries. So I'll ask you to go through those tutorials if you are attempting to solve a problem something like this. Okay, but I'm not gonna show you this part or this aspect of it today, because it's going to take a lot of time and we need to do a lot other things as well. So I'll start the next part, model. Again, be patient. It's going to take some time, and you can see the status in the left bottom corner about what it is doing right now. So it's saying that it is starting the mechanical, so let it start. Can we disable the closed captioning?
You can turn it off. If you click on the bottom where it says closed captioning, you can turn it off.
On the bottom.
So you should have somewhere where there's a bar on the bottom that shows the zoom.
There are 3 dots.
Not the 3 dots. To the left of it, there should be something about live transcripts.
I can't see any.
Try taking your mouse all the way down to the bottom. It might be hidden. Or in your other screen. Because you're full screen, it might be hidden. Or go to Zoom.
Yeah, I'll go to Zoom. No. All right, fine. I learned this thing, another thing to learn. You need to close this one, close this, make sure that you maximize the window. Again, make sure the units are consistent. So in this environment, you don't have an option at the top. Rather, if you look at the bottom right side, you see what the units are. So it is already showing you the metric units in millimeters. So that's fine. So what we need to do, the first thing, we are going to be doing the mesh. So you can see that there is a bolt mark on the mesh already. Click on this. Okay. So the ribbon bar will change according to the mesh environment. So you have all these options, method, sizing, refinement, and stuff like that to play around with. You can do it in your own time, and you'll have to do it because like the results which we are going to be getting today are not very accurate. I give you fair warning that it's not very accurate results. You will have a lot of difference if you start refining the mesh. So again, the purpose of today is to show you the functionality of the things, not the accuracy of the results. Okay. So what I'm going to do to create the mesh, I'll just simply click on generate. And this small window will open up and it will generate this mesh. Now it is a tetrahedral mesh. So if you rotate it, you can see that the mesh is not very fine and it has a lot of transitions. It is not composed of quadrilaterals, rather you have tetrahedrons. Why it has selected tetrahedrons? Because since we had a circular surface here, so tetrahedrons deal with the circular surfaces better. But we have learned it in the previous example as well that quadrilaterals do well with this as well. And I would recommend you to go with the quadrilaterals thing. And I want you to explore it on your own, how to change the mesh from tetrahedrons to quadrilaterals. So what are these words? The easy way of distinguish between them is that tetrahedrons are composed of these triangular faces. On the other hand, quadrilaterals will have what it is called, 4-sided faces. Okay. So now, beside the mesh, we have a check mark, which means that the meshing has been taken care of. Let's sorry. Let's see what the next step is. We'll continue in the mechanical interface to define the physics. We need to assign the material properties, very important step. Then we'll apply the boundary conditions. And we'll make sure there is a new thing which we didn't take care of last time, but we'll need to make sure that the large deflection option is on. What this is, whether it makes a difference or not, the only thing which I will add about this option is that whenever you are tackling with large plastic deformations, okay, in FE, in any FE analysis, you need to make use of this large deflection option, because either you are in Abacus or in ANSYS or whichever FEA software you are using, there are two different formulations already built into it. And the reason of these two is like one of the formulation is for those cases where the deformations or deflections are not going to be too much. These formulation, if you recall that whenever we are doing the kinematics and kinetics and stuff like that, we sometimes say that we assume that the displacement is a small. And when we say that, we make use of the relationship of S is equal to R theta and stuff like that. Okay. So those cases are the ones where we are assuming some stuff, although there may be some curvatures and stuff, but we are assuming that they are straight lines because it is so small that we can safely assume them to be straight. That is one of the aspects of this large deflection. There are other assumptions which are taken when we are solving for mechanics at the back end, when you are solving the stress analysis equations. So the treatment when the deformations or deflections are small are different than the treatments when the deformations are higher. Okay, so I suggest that if the strains are beyond 0.1 in your case, and in certain cases or certain applications, even if it is beyond 0.02 or 0.05, make sure that the large deflection is on. Okay, so quick overview. We need to assign the material properties, we need to assign the boundary condition, and we need to make sure that the large deflection is on. How to do that? Let's quickly do it. For the material application part, if you recall, we can assign the materials in either of the two ways. One way is, which we learned last time, that we just right click on these materials under the material folder and click on create material assignment. Other way is, let's see whether it's gonna work today or not. Let's see. By clicking on the geometry features here. So one of the geometry feature is this solid here. You can see that it is asking you for material assignment. So if you click here, voila, last time it was the materials we selected were not appearing, but this time they are appearing. Okay, so this solid is basically this cubic part, or my matrix part. So the matrix is made out of titanium alloy, so I'm going to select titanium alloy. Okay, then the other solid, this solid, since this one was the matrix, this is definitely the inclusion part. So the inclusion is made out of tungsten carbide, so I'm going to select tungsten carbide here. Okay. Sorry. So the material assignment has gone fine. The next step is to define the boundary conditions. Before going into the boundary conditions, let's just, for the sake of sanity, check, see which material is assigned where. So click here, you can see that titanium alloy is highlighted here as the green color. So it is telling me that this part is made or assigned the properties of titanium alloy, and this part is assigned the properties of tungsten carbide. Another thing which was automatically imported here, Christopher, I guess in the tutorial which you have followed for the symmetry thing, I'm unmuting you if you have anything to add. Yeah, so in that case, you did the symmetry conditions, you created a geometry, already a quarter geometry, and assigned the symmetry or created the symmetry here in the mechanical environment. But since we have already generated the symmetry condition, created the whole geometry, and then created the symmetry conditions in the design modeler, that things or those settings are already automatically imported here in the mechanical environment. So you don't have to explicitly define that these faces has some kind of symmetry. Okay.
That's probably where I should have generated the symmetry originally in the geometry.
Not necessarily. You can do in either of the two ways. Both of them should work. Both of them should work. All right. So, okay, now the viewer muted. Cool. So, where I was. Yeah, so the symmetry is already taken care of. Wait a second. Now what's next? We are supposed to assign the boundary conditions. So what symmetry condition is? Let's discuss a bit about it. Not in detail, but just a brief overview. So for this phase, the symmetry is about x-axis. So what does that mean, or how it actually sure Lisa, how it actually creates this symmetry thing. So it doesn't do anything, but it is just another displacement boundary condition, in which what it does, that it will enforce the condition that the displacement in the x-axis, the axis which is perpendicular to this face, the displacement value is going to be 0, as well as the rotation about z and y axes will be 0 as well. So these three things will be assumed as or enforced as 0. So there will be no deflection in the x direction. There will be no rotation about y or z direction either. So displacement in the y can happen, displacement in the z axis can happen, rotation about x axis can happen on this surface, but not the other three things. Okay. Similarly, you have symmetry about, if you have symmetry about, I don't know what's happening here. Yeah. Now, if we have symmetry about, if we are looking at this phase. So now for this phase, the symmetry is about z axis. So the displacement in the z direction will be 0, will be enforced at 0. It will not allow any kind of displacement in the z direction. The rotations about the x and the y axis are constrained to be 0 as well. Only the motion in the y and x direction can happen, and the rotation about z axis can happen. So now, for example, in this particular problem, when I apply, since we were asked to apply a displacement of 0.2 millimeters on the face perpendicular to the x-axis, because my problem statement was that there is a displacement of 0.4 millimeters in the x direction. For this case, what was actually happening, that this surface was fixed. Okay, it was not allowed to move, and this face was moved by an amount 4.4 millimeters. So the change in length of this side was 0.4 millimeters. But since we have plotted or running an analysis only on the 1/8 of the cube, okay, so we are gonna be modeling only 1/8. So assume that if I move this side by an amount of 0.2 millimeters, this end, since it has a symmetry, this end has moved by an amount of 0.2 millimeters as well in the opposite direction. So this is what happens if I apply a symmetry condition on the center plane. Okay. So if I want a resultant displacement of 0.4 millimeter to happen for the whole cube, if I'm creating only part of the cube, I have to scale the amount of displacement here to take care of the automatic displacement happening on the other side as well. I hope nobody has any confusion with this. If you have any confusion in understanding this concept, ask me, I'll repeat it. All right, cool. So that's why I am applying a displacement of 0.2 millimeters on the face, which is perpendicular to the x-axis. So let's go back. So this is the face where the displacement is supposed to be applied. I'm gonna go to the static structural. The ribbon bar will be updated according to the boundary condition environment. You have different boundary conditions here. If you recall, last time we applied a pressure boundary condition because this is what we knew in the problem. But in this time, since we know that we are, for example, running a uniaxial tensile tension test, and in that tension test, it is the displacement control test. So the displacement is the thing which we know. So we are going to be applying displacement in this case. So this is the option for the displacement. It is asking you for the geometry, which means that it is asking you for where you want to apply this displacement. So I'm gonna select this face. If it is not already selected, make sure that you have this option click, which will allow you to select the face. Okay. So select this. You can also apply displacement only on the edges. If you have only one edge, which is on which you know the displacement, select this edge, and it will apply the displacement only on this edge. Okay, but since we need to apply it on the whole face, I selected this face thing, and it is allowing me to apply the displacement on the face. You may want to apply the displacement on this corner face, on the corner vertex as well. Vertex is another name for the point in CAD. Whenever you are calling a point, is called a vertex. All right, so in this case, since we need to apply it on the face, we have selected this option and selected this face, click on apply. We can apply displacement in the X, Y, and Z direction. Since we need to apply it only in the X direction, and we need to apply it by an amount of 0.2 millimeters. So it will apply displacement in this direction by 0.2 millimeters. Okay. There, if you look at it carefully, there is a thing called ramped written here. Ramped means that it is going to apply this displacement monotonically. The rate of increase or the velocity is going to be constant. Okay, it will apply this displacement with a constant velocity. If that is not the case in your particular analysis, what you can do, you can use these options. You can use a function to define how the displacement is going to be applied with respect to time. You can put some tabular values as well. Okay. Why do you need that? You may want to do that if you are adding the thing in steps or something like that. Okay. So that's the only boundary condition that we need to apply. In this case, the rest of the faces are free. They can move, they can rotate, they can have any amount of, and since they are free to move and rotate, they won't have any kind of stresses on these faces or the forces on these faces, on the tractions. Since these things are already constrained by the symmetry conditions, we don't have to apply any other boundary conditions. Next step is, if you recall, I told you that we need to make sure that analysis is a large displacement is already selected. To change that setting, I need to go to the analysis setting here. Okay, make sure that you click on this analysis setting first. You can change the settings for the analysis which will run for the solution. Okay, so there are a lot of options here. Some of them are how many number of steps you have. We only have one step. So there's a small difference if you are coming in from LAMPS tutorial yesterday. The definition of step in the LAMPS is different. The definition of steps in ANSYS and as well as Abacus is different. So in this case, we only have one step. We can have different number of increments. In this case, the number of increments is called sub-steps. So sub-step is going to be the point in time where the data will be output or the results will be provided to you. So if you want a lot many instances of output, and in this case, you may want to have a lot of outputs at each time step. Then you can change this thing. Here, that how you want the time stepping to occur. There is a whole lot of details involved in it. I won't go into the details of it. You can always look into the documentation of this to see how these things work. But for now, I am leaving it for program controlled, and I will be on the mercy of the software to see where it will give me the results. You will appreciate this in just a little while. What does it mean by that? For now, just make sure that you select this large deflection to be on. Make sure that large deflection is on, because we'll encounter strains of around 0.1 strain values. All right. Anybody has any questions up till this point? I guess the most important part about in this case was understanding the symmetry condition, symmetry boundary condition. If you have understood that, then I doubt you will have any questions. All right, cool. Let's see what's the next thing we are supposed to do. Okay, so now we are gonna be running the solution, and we'll be looking at the results. Let's see what results we are interested in. So we are going to be calling for the results of deformation. We'll be interested in to know the equivalent stress distribution. We'll be interested in seeing the equivalent strain distribution in the body as well. We'll be interested in to know what is the distribution of equivalent plastic strain. Okay. Also, we'll create some probe values. I'll explain why we are doing that in just a little while, and what they are. If any of you has done uniaxial tensile test, most of the recent ones automatically gives you the values of stress and strain if you provide these dimension of the specimen, but otherwise, ideally speaking, they are just measuring the amount of displacement of the one of the heads, and they have a cell there, load cell there, to measure the amount of force. So the output value is the force and the displacement. Okay. So think of this probe as this measurement system. We will measure how much reaction force is there on the face, on one of the faces, the face which is perpendicular to the x-axis, because this is where we are applying the displacement. And we'll be interested in the displacement of the x-axis as well as y and z direction. I'll explain why we are interested in the y and z direction in just a little while. Okay. Also, we'll solve the results and then look at the solution of the deformation and the stress distribution. So let's do this then. So in order to establish the solutions, you need to click on the solution to update the ribbon bar. Now the ribbon bar is showing me how to add each of these results. We are interested in the total deformation. As I told you, we are interested in the equivalent strain. So this is going to the equivalent total strain, or it is calling it equivalent plastic strain. We will be interested in equivalent plastic strain as well, because I know that the system is going to go into the plastic region. Okay. So I want to have a look at where the most of the plastic deformation is happening. Okay. Sorry. So that's why I've added this equivalent plastic strain output as well. In addition to that, I want to have a look at the equivalent stress distribution as well. About the probe thing, you can add the probes by clicking here. So this probe is a bit different. If you recall, the probe which we used last time was used when the result was already out, and we have a contour plot, and we want to see what is the value of the contour or the value of the quantity which was plotted at a specific point. This probe is a bit different. This probe is like a meter. We are adding a meter to measure certain quantity, okay, beforehand. before running the calculation. So both of these are called probes, but their functionality is a bit different. Okay, so I'm going to add a probe for reaction force. Okay, so where the reaction force we are looking at? We are interested in the reaction force perpendicular to the x-axis, because this is the face where we are loading my specimen. Okay, I'm interested in the displacement or the load in the x-axis. So there are different ways of defining where you want to measure the reaction forces. You can select it by geometry, you can select it by contact region, you can select it by remote points, stuff like that. But right now I'm going to select it by boundary condition. There is a boundary condition which we applied, which was displacement. Displacement was applied on this face. So if I select this as displacement, it is going to be applied on this face. Okay, then I want the probes for the displacements as well. How much displacement is happening? Why do I need that? I want to calculate the strain in this RVE in the x direction, as well as I want to calculate the value of stresses as well. So I have the value of reaction force. In order to convert it into stress, I need the cross-section area. Okay, in order to know the cross-section area, I need to know what is the dimension of this side and what is the dimension of this side to give me the cross-section area. I can know this values because I already know what is the starting length of this side. The length was 1.75 millimeters because it is only half of the total length, and this length is 1.75. I'll subtract or add any deformation which is going to happen to these sides to calculate the updated area, updated cross-section area of this face. Okay, so that's why I'm going to add the displacement of this corner vertex as well, and the x displacement of this vertex is going to give me data to calculate the value of strain. Okay, so probe, deformation. In the deformation, we need to select a geometry where we want to find the displacement, the deformation. As I told you that I'm interested in the displacement or the deformation of this corner vertex. I cannot select it right now because the selection procedure is face. So I can only select a face right now. But since the displacement is required for the vertex, so you have to click on this one first, this option, so that you will be able to select this vertex. So now you can see that whenever you hover over this small corner, your cursor will change. So now cursor is showing you that you are over some corner vertex. So click on this and click apply. Now it is asking you what displacement you are looking for. You cannot select all. I don't know why, it is stupid, but you cannot select all. You have to select them one by one. So I'm adding one on y-axis, quickly adding one more on the same point for z displacement in the z-axis, and adding one more on this corner for x-axis. If somebody works it out why it is not allowing me to find all, do let me know. I'm going to rename it to some meaningful thing to distinguish between each of them. So the deformation probe Y, deformation probe Z, deformation probe X. All right, my solution setup is already set up. We have set up the whole thing. One thing I forgot, and I forgot to mention it in the slides as well. If you recall, we have two distinct phases. Okay, one was tungsten carbide, the other one was titanium alloy, and there was an interface between the two. And whenever we have interfaces, or we have more than one bodies, you have to define the interaction between the two. You have to define how they are going to behave when they come in contact with each other. Okay, so I forgot to mention that in the slides as well. Unfortunately, I'm sorry for that. So when we were, I don't know what is happening here. Wait a second, let me minimize and maximize again. And now is a good time to save it as well. Come on. Why does not maximize? Wow. I think I need to close it and open it again. I hope I haven't closed the workbench thing. All right, cool. So I was saying that it's still. All right, so I was saying that I forgot to mention the interaction part. And there was a reason for that, because like if you recall, when we were creating the geometry in the design modeler, it asked me what is going to be the interaction between the two new surfaces which will be created. And if you recall, we told the system or the workbench that they are gonna be merged. So merged means that it has created a contact region between the two, and the contact region was, the type of the contact region was bonded. Okay, what does the bonded contact means? The bonded contact means that these two surfaces will have the same deformation in all three directions. Okay, so there's going to be, let me try and draw it or explain it by some drawing here. Okay, let me add a slide for interaction. Slide or contact. So let's assume we have these two bodies. Let me change the color of this one. Okay, make it correct. Okay, so we have these two bodies and they are in contact with each other. So the contact, since these are 2D bodies, the contact is an edge. But if just try and visualize it, if you have a 3-dimensional body, the contact is going to be between two surfaces. Okay, so there are certain things which define different type of contacts. One of the and there are effectively two physical quantities which almost completely define the contact between two regions for most of the applications. One of the thing is the displacement and force perpendicular to the surface, and the other thing is let me name it quickly. So we have to have traction, let's call it traction, and let's call it traction in y direction for the sake of simplicity, and displacement d in the y direction. Okay, similarly we have the same two things in the x direction as well. Okay, so we have different type of contact definitions here. We have a bonded contact, we have a no separation contact, we have frictionless contact, we have rough contact, we have a frictional contact. Okay, so what are these different types? Let's start with the bonded one. So bonded ones means that whatever is going to be the displacement of the surface of the bottom body in the y and x direction, exactly the equal amount of displacement is going to be of the surface of the top body, which is in contact with the bottom body in both these directions. Okay, and since we are enforcing these constraints to motion, there may arise some kind of tractions in the in the X and Y directions as well. Traction is something like force divided by the cross-section area. Okay. Then we have no separation contact. No separation contact is not available in all these softwares. It is sort of unique to ANSYS. So what does it enforce? It enforces that the displacement in X and Y direction will be same for both the body, both the surfaces of each of these bodies which are in contact, but there will be no reaction forces arising because of this constraint. Okay, because from elementary engineering mechanics we know that if we constrain the motion of any body in a certain direction or rotation in any direction, we are introducing some kind of reaction forces there. And this is going to happen in the bonded surface, but not in the case of no separation boundary. So the no separation boundary will enforce the displacements to be equal on both the bodies, but it will not let any reaction forces arising as a result of this. Then comes frictionless contact. So what does the frictionless contact will do? The frictionless contact will not allow the displacement perpendicular to the surface. So dy will be enforced to be 0. Okay, but the displacement dx, the relative displacement dx, make sure that these things are in relative terms, relative to each other. So the relative displacement in the x direction will be 0, and as a result of the displacement there will be no traction force appearing as a result. So tx will be 0. Okay, since we are allowing some motion, relative motion between the two, so tx will be 0. Friction force will be 0, but because we are constraining the perpendicular motion, there will be some traction in the y direction. I know it is a bit overwhelming. I'll enlist all these things in this slide, and we'll update the course slides and we'll share it in the Slack later on. For the rough surface or for rough type of boundary condition, what's going to happen? It is not going to allow the displacement in the x direction. As a result, there will be some kind of traction appearing in the x direction as well. How it is different to the bounded condition, I still need to check it, because I don't know how it is treating the rough surface here, because we don't have it in Abacus either. Frictional means that we know the amount of friction between the two surfaces. Okay, so we'll provide some kind of friction coefficient between the two, and it will allow the relative motion of the two in the vertical, in the horizontal direction, but it won't have 0 force. Rather, it will have some friction force as a result of the relative motion between the two. All right, for our application, we are assuming that these two surfaces are welded together. They cannot have any relative motion in the y direction as well as x direction, or I'll say that it will not have any relative motion in the direction parallel to the surface and the perpendicular to the surface. As a result, there will be some kind of tractions appearing as well. Okay, so that is the contact established here. Since we have created the geometry this way, it automatically selected between which bodies the contact is happening and between which faces the contact is happening. If you haven't created it this way, and you have created these bodies separately as a separate body, you may have to explicitly explain which of the faces are coming in contact and which of the bodies they belong to. Okay, again, you can practice it in your own time, and I'm sure that it is not a very difficult concept to take hold of. All right, once everything is done, we are ready to run our solution. So let's click here and click on solve. And while it is running, if you have any question, do ask me now. Let me grab my water bottle. Probe. Okay, I'll explain the probe once I'll get the results. Just give me 1 second. Okay, would one of these options allow for the two bodies to separate and come into contact repeatedly? The frictionless contact will allow it. Okay, but make sure that this going away and coming together thing doesn't happen at a very high frequency, because if it is happening at a very high frequency, your problem is no more a quasi-static one, rather it will become a problem of transient analysis. So you will have to run a transient structural case for solving that. Okay, but since if it is not like going away and coming together very fast, you can run it in quasi-static, and the condition for that, or the contact condition for that, is going to be either of these three things. It can either be frictionless or rough or frictional. All these three options will allow separation between the two bodies. I hope I have answered your question, Brendan. Cool. Okay, so Joshua, you asked that, can I explain the probe again? I'll explain it when I'll show you the results. Just give me a second. Advait said, can you tell me again from where did you add the connections? So I haven't added the connection. It was already established when I imported the geometry from the design modeler. It automatically created it. But if it has not, and you want to create it explicitly yourself, so what you need to do, you need to right click on model, okay, and click on insert, and it is not showing me any option for that because it is already selected. Yes. So since the connection for it's already added here, if it was not, you need to click on model, right click on the model and select the insert thing, and you'll have the option of connection here. So you need to click on the connection and it will add the connection here, and then you can start adding connections one by one. You can have more than one connections in the same analysis. You can have 3 or 4 or 5 bodies, and each of them can have different contact regions. Okay, once you have the connections added, now right click on this and click on insert and click manual contact region or contact tool. You have different ways of adding this. What I would do, I'll just click on manual contact region. It will be added, and then you will add the connections manually between the two. But I strongly suggest that try and create the geometry the way I did. So start with a single body, okay, and then cut the body or slice the body there and there, so that these connections are made automatically for you. You can explicitly do that using these options I told you. Does it answer your question? Cool. Okay, so the results are here. Let's have a look. So I have a total deformation results. Just give me a second. All right, so what's happening? We have the results. If we revolve it around, rotate it around, we can see that the maximum displacement is on this face, and this is the logical, it has a very logical reason as well, because we applied the displacement on this face. It was constrained to move by an amount of 0.2 millimeters, and hence the most displacement is happening on this face as well. And since this has the symmetry condition applied to it, I'm sorry, symmetry condition applied to it, that's why the values of displacements are very small on these faces. Okay. Then equivalent elastic strain. Let's have a look at the equivalent elastic strain. We all know the definition of the strain. strain is nothing but displacement or deflection divided by the original length. Okay. When we are looking at it, it is a contour plot. Let me make it a bit cleaner. It's a contour plot. Contour plot means it is showing me the distribution of the elastic strain value, equivalent strain values. We can see that the blue region has the strains within the range of 1 exponent minus 3 to 3 exponent minus 3, which are very small strains, as compared to the red region where the strains are 0.01 between 0.014 and 0.15, which is relative to this one quite high. Okay, understood? So we are seeing that the value of strains is quite high in the region where we have titanium alloy, and the inclusion region has very small strains. And there is a very strong jump when we go from the inclusion to the matrix phase. Does anyone want to comment on that? Why this is happening the way it is happening? You can raise the hand so that I'll unmute you. Don't try to type it. All right. So if you recall, I'll quickly go back to this slide. If you recall that the stiffness of the titanium alloy was very small as compared to the stiffness of the tungsten carbide. Okay. The inclusion is made out of tungsten carbide, whereas the matrix is of titanium alloy. So since the stiffness is very small here, most of the deformation is happening in the matrix phase rather than it is happening in the inclusion phase because of the difference in stiffness. Although the amount of, because of the higher stiffness, the strains are smaller in the inclusion phase, but if I click on the equivalent stress, the tables are turned now. The amount of stress in the matrix phase is very small, but most of the load is being borne by the inclusion phase. And this is where the strengthening effect of composite or reinforced composites come from, that we reinforce a softer material by including the inclusions of stiffer material. Does it make sense? Still no response. Come on, I assume that a better response from the materials guys. Cool. All right, so you can see the difference in the or the distinct division between the stresses and the strains between the two phases. So the harder phase is rather it's a stiffer phase is taking more of the stresses, but the strains are smaller there. But in case of strains, it is the other way around. Plastic strains. You see that as soon as I click on the plastic strain, the inclusion is become transparent. Anybody care to tell me why is that? One of the reasons is that we don't have any kind of plastic displacement or plastic deformation in that region. You are right, perfectly right. But there is another thing that when we were establishing the material response or the material properties, if you recall that we didn't provide any kind of plastic properties for the tungsten carbide. Let's not rely on the recalling part. Let's open it and see what it is. So in case of titanium alloy, we have plasticity explicitly explained here. We have a bilinear isotropic hardening, okay, which is explaining how it is gonna behave in the plastic region. But if I click on tungsten carbide, I didn't included any kind of plasticity here. The plasticity model is not there. We have the failure model, but not the plasticity model. So the software doesn't know, ANSYS doesn't know how tungsten carbide is going to behave in the plastic region. That's why as soon as when I'm looking for the plastic response, it has just turned it transparent. So of course, within the range which we are talking about, it would not have gone into any kind of plastic deformation. So we don't even need to add that kind of response here. But if we had included anything, it wouldn't have gone into any plastic deformation. It would have shown me a blue color here, which means that we don't have any plastic deformation. Okay, so yes, it is assuming that it is going to be elastic till it fails. It won't undergo any kind of plastic deformation. All right, cool. So we have looked into the distribution of the deformation. We have looked into the strains, plastic, elastic both, and the stresses as well. Now what I'm interested in the output of the tensile test. Since we have kind of run a tensile test, I'm interested in the output of the tensile test. The result of the tensile test is in the form of either force displacement curve, and then we calculate the stress and strain out of it. So in order to do that, I have created a small Excel sheet, and where it has gone. Cool. Let me have a look. I should have saved it somewhere. I have created a small Excel sheet to calculate these values. I will share this sheet with you. I don't know whether I shared it with you or not. Where it is, file, save as. So it was located in the ANSYS folder, but I couldn't locate it. Why? Okay, it was in. Yeah, this is the one. Here it is. Cool. So I have created a small Excel sheet for the calculation of stress and strain. If I go back here, now I'm going to answer you for the probe thing. Somebody asked me about the probe. So if I click on the force reaction probe is now telling me, if you look here, and if you cannot, you can go between the graph and the graphical annotations and stuff like that. And if it is not already appearing, you can have a look at the tabular data. So this probe is giving me a tabular data, and it is giving me the values of the reaction forces on this phase in the X direction, Y direction, and Z direction, and the total reaction force. Okay, you can see that the reaction force in the X and Y directions, Y and Z direction is negligible. It is almost zero. And we have a huge reaction force in the X direction. Okay, so I'm going to use this force to create my force displacement curve. Okay, then we have a deformation probes on these corners as well. So what these deformation probes are doing, it's giving me the values of displacement in X, Y, and Z direction of this particular corner. Okay, so this deformation probe Y is telling me how much displacement it has undergone in millimeters in the Y direction. Same for the Z direction, same for the X direction. So I can use the displacement of X direction and the reaction force in the X direction to create my force displacement curve, and you can plot it anywhere. I have plotted in the Excel sheet here. Okay, how you can do it or how you'll extract that data. What you will do, you'll just highlight this thing, and I'm used to Control C and Control V thing. So I'm just gonna press Control C. It is gonna copy it, but this is not gonna be copied on your system's clipboard. Rather, it is gonna appear here because you're in a VNC remote desktop connection. So you need to access that stuff which is copied using this option here. So it may be appearing on this side, but in I was having difficulty, so I just turned it towards this side. So I'm gonna highlight everything by pressing Control A, Control C once again, and then I can paste it here on my Excel sheet. So this is the displacement. Then the reaction force I highlight the reaction force in the X direction, Control C once again, you can see the clipboard values have changed. Control A, copy it once again and paste it in your Excel sheet. I'm going to highlight these two things, click insert and add a scatter plot, which should tell me, and of course it has started from 0, 0. So add these 0, 0 values yourself. So this is the curve, which is the response, this force displacement response for your composite case. Okay. We can see that if you highlight it, we only have very few points, and this upward region is not the actual case. It is only happening because Excel don't have a data between these 2 points. So it just try and extrapolate the things between these 2 points. Okay, it's not the real case. This bump is not a real result. It is just because of the interpolation happening in the Excel. So just imagine it to be a straight line between these 2 points and a straight line connecting all these things. So this is the response, force displacement response of your composite material. Okay, how to convert it into stress and strain response? If I go back here, I can similarly copy the values of the deformation in the Y and the Z direction, and I can copy it in Excel sheet here. Okay, and then I can use this formula, which I've already put into this Excel sheet. I'm going to share this sheet with you. So what's happening here? I have pasted the reaction forces in the X direction. Let me rename it to FX. Reaction force in the X direction in this column. This column relates to the deflection in the Y direction, deflection in the Z direction, deflection in the X direction. Strain is calculated as a logarithmic strain. Logarithmic strain is nothing but the final dimension of the body divided by the original body. Okay, a question. Is this generally how you can find the stress strain curve for a specific shape for material with better meshes? Yes. If you don't have a lot of, let me have a look. If I look at the deformed shape, by the way, if you look at a thing called scale, so whenever you plot something, ANSYS try to show it in a scale so that you have better visualization. This displacement is not, or the deformed shape is not shown to scale. Okay, so in order to make it shown to scale, you need to select this option, true scale. Okay, now if I click on the X direction, you can see that the faces parallel to the Y and Z direction axis is not parallel, or like they are not straight faces anymore. Okay, but they are not very different either. Okay, they are quite planar. Okay, so we can safely assume that whatever the cross section area we have here, we will have a cross section area here as well. If you do not have that, what you can do, you can measure the cross section area at a couple of points or a couple of faces along this line, and then take an average of that cross section area to calculate the value of stresses. But for a strain, it will be the same for all of these cases. Okay, so I'm assuming, although it's not planar anymore, but I'm assuming that the cross section area is same throughout the lengthwise. Okay. Oh, we have ran out of time, but I think we can go beyond this thing. I'm sorry, Lisa, that we are going beyond the time. I hope it is not a big problem. Are you there? Oh, cool. All right, let's make use of these things, because I just got too involved in these small things, and there was a reason, because these things are important for you guys as a materials engineers. Okay, so what we have done, we have used simple relationship for calculating the logarithmic strain. So the logarithmic strain is nothing but the final dimension divided by the original dimension. Okay, so final dimension is nothing but original dimension plus whatever the deflection has happened there. So I've calculated the strain by using this small formula in the Excel sheet. I hope most of you already know how to work with the Excel sheet, and if you don't, as I said, and I'm going to share this Excel sheet with you guys. Then the stress is calculated. If I double click on this, the formula I've used is the force in the X direction divided by the final dimension in the Y axis and the final dimension in the Z axis. So I've taken the product of the Y and Z dimension to create, to find out the cross section area, and divided the force by that cross section area to calculate the value of stress. So effectively speaking, since I am using the updated area at each time step as the force is increasing, this value is the value of true stress. Okay, this is not engineering stress, this is true stress. Okay, so this, when I plot this stress and strain response, the result is here. This is the stress strain response, and you can see that I am not having that artifact. The reason being that I explicitly asked for the outputs at more than these many points. So here I only have 4 data points, but I have asked for 100 data points to create this thing. So this is how I have plotted the result. So the blue line is the plotted result of the analysis which we just did. Okay. Now let's have a look at a quick comparison between all these things. So this orange line is for titanium alloy on its own. Okay, this is the stress strain response of the titanium alloy on its own. This is something which we have already provided as a material property. Or if you want to have a test, what you can do, you can very quickly go here, and if you recall, I assigned the property of tungsten carbide to this phase or this portion. What you can do, just try and change it, just save the thing, just save the results and everything first, and then change the property to titanium here as well. So now this whole cube will be made out of titanium alloy. Okay, and run the same analysis again, and you will, if you plot the stress strain response, it should overlap this orange curve. And this is how I have created this. Or if you go back to the workbench, you have this properties of titanium alloy here. This is the curve. You can just copy these values from here and create your own curve on your own. Okay, it is going to overlap with this orange curve, or at least it should. Okay, so this orange curve is the response of just the titanium alloy. This gray curve is the stress strain response of tungsten carbide. This yellow curve is plotted using the formula I used earlier, and I mentioned it to you, using the volume fractions. Okay, finding out the volume fraction thing. So this is this yellow curve, and you can see, and this blue curve is the actual composite. You can see that in our case, we have a huge difference between the homogenized results and the actual results. So this blue results are more close to the reality. But keep in mind that this blue result is not the accurate result. It has a lot of error in it. Reason being, the discretization we have done is very coarse. We have to refine the mesh to get a better results. So one of the exercises which I have suggested to you for this problem is to refine the mesh and run the analysis again and see how much deviation you are getting between the two. Okay. But one more important aspect of it is, so one of the motivation for doing this analysis is that the homogenized results is not the true result. They are deviating it a lot from the homogenized results. Okay. The other thing is that even if you can calculate the homogenized results, you could not have predicted how it will behave during the plastic part. So you can do the homogenization in the elastic part, but it would have been very difficult to predict what is going to be the plastic response. For this plastic response, you can you definitely cannot use homogenization. You will have to use the HLB's thing there. And you know how complex the HLB thing is. So this is your motivation here, to use the FEA. So this is what I told you, that either you use it for the cases where the analytical result doesn't exist, or you use it for the cases where the analytical result is too complex to calculate by hand. Okay. So this is probably the last slide which I was supposed to discuss with you, which is the discussion of the results and comparison between the numerical and analytical findings. And of course, since we have done this thing, so save it at the end where it is. So since we have gone through everything, we have done all these steps, make sure you save your project, yes, so that all the results and data will be saved. And this is all we have to discuss in today's session. One more thing, I mentioned that you can have, start writing your questions if you have any. I mentioned that you may want to have result output at more than one point. So for doing that, what we need to do, go to the solution, sorry, analysis setting. And here you see that there is an option called auto time stepping. So go there and click and switch it off. Okay. Now you have switched off the auto time stepping. It is asking you how many sub-steps you want. Never give the number of sub-steps less than what it has calculated for the automatic result. So if you recall, we have 4 sub-steps there. If I want to have more data points between these, yeah. So we didn't have too many data points, because of which we were not getting a smooth curve. So we definitely have to increase the amount of data points. So if you want to increase the number of data points, go beyond this number. So you can enter 20, 30, 40, 50, whatever amount of data points you want. Just add it here and run the analysis again, and it will give you the results at each of those data points. All right, so that's all from my side for today. If you have any questions, I can answer that. You can type it in, or you can raise your hand so that I'll unmute you and you can explain that question in detail. Okay, Advait said that how to get stress versus global strain at a particular point, region like near to the particle. Okay, let's rotate. Let's answer this thing. If you, the results have lost because I've changed the settings. Let me quickly run this analysis again to answer you. Just give me a second. I want to discuss one more thing, that there is another reason for the huge deviation between the homogenized result and the result of the composite. If you look here, if I look at the distribution of the plastic strain, you can see that the plastic strain is concentrated around here somewhere. Around the inclusion, we have concentrated plastic strain. So what is happening, that because of this inclusion and the difference in the stiffness of the two phases, we are getting a stress concentration around the inclusion, which is inducing localized plastic deformation. And since we have localized plastic deformation around the inclusion, it is making the stiffness go down. So this stiffness is not for any element. So you need to make sure, or like try and establish this thing in your mind. It is a bit It is a bit of a difficult concept to grasp, but there is a global value of stress and strain, and there is a local value of stress and strain. So we have localized plastic deformation, but if I calculate the global values of stress and strain, we can see that this thing is still in the elastic region, but it not necessarily has to be elastic everywhere. We may have some kind of localized plastic deformation happening somewhere around the inclusion. So that is one of the reasons that we have such a huge deviation from the homogenized result. Okay, because one of the phase is has started to undergo plastic deformation in the localized region. Okay, so that's one of the things. I don't know whether I am able to explain this thing to you or not. Otherwise, so we have the results now. So you said that can we plot the results of stress in a localized region and the global strain? Yes, you can do that. How to do it? You just click on probe and select one of these elements. So what it does, it starts to show you the values of stress. What are we plotting? Sorry, strain. So if you want to plot the stress, so this is the stress. So if you want to, you're interested in getting the value of stress in a vicinity of the inclusion, so just probe the value in the vicinity of it. So you calculated the value, you start to get the value in that point. Okay. So this is one of the way of plotting the localized values here. There has to be a way of calculating the values of the stresses at each time step as well. I'm not sure how to do that, but of course you can look into the documentation to find out how to get the tabular data of stress in each of these elements as a tabular form. Or you can always create a probe. So if I click here, I think I can create a probe for stress. Yeah. So create a probe for stress if you are interested in knowing the value of stress in the vicinity of the inclusion or the area of interest. Okay, because most of the things are going to be happening around here. Anything else? All right, I safely assume that nobody else has any question, and I have answered all of the questions. So somebody said that how to get stressed versus, okay, so I have answered that one. The next meeting starts with, okay, cool. So let's quickly go through some of these exercises I'm prescribing you to do. Again, as I told you that I have shared the files which I worked on in the last session in the Scratch training intro ANSYS folder. So you can go to that folder again for the today's on the files which I worked on today. I've already uploaded it there. What I'm expecting you to do, and I strongly ask you to do it to practice the concepts you have learned today, is to try and refine the mesh. Make sure refine it to a certain degree. Do it by either by sizing the element size, decreasing the element size, and refining it around the inclusion. One thing, and again run the results and see how it happens. Even more important to that is to play around with the volume fractions. Okay, how to play around with the volume fraction? I'm asking you to reduce the volume fraction to 0.05. The volume fraction we worked with was 0.1. Try and reduce it to 0.05. I'm very confident that the kind of material response you will get is going to be very, very different than the response you have seen here. Reason being that since the inclusion was quite big, we were creating a strong localization around the inclusion, which was inducing the plastic deformation to start prematurely, which decrease or make the material less stiff. Okay. Another volume fraction you may want to have a look at is 0.2. So I urge you to come up with these or generate the geometries for these two volume fractions and see how they compare with the volume fraction of 0.1. So this is some of the things which material scientists do all the time. So they try and change or play with the volume fraction of the precipitates and see how the material response changes as a result to that. So how to change that? If you just plug in the value 0.05 here and the value of 0.2 here and calculate the value of S, your inclusion size will remain the same, but the value, the size of your cube will change. So in case of 0.2, it should change to almost half, reduce to almost half. And if you change it to 0.05, the dimension of the S or the value of the S will increase a lot. Okay. So that is one of the exercises which I asked you or urged you to do. And I very strongly recommend you to do it for the practice to learn or to relearn the concepts which we did today or which we covered today. Another thing is going to be to try and add your own materials. If you are working in any specific type of composites, try and put in those values of the composites in it. I told you how to add the materials. For the elastic part, it is very easy. Just put the isotropic elasticity and that's the only input it requires. But the results are not going to be that interesting if you are only dealing with the elastic part. To make it more interesting and more useful, you have to put in the plastic properties of the matrix phase as well. Okay, because my understanding is that the matrix phase will always be softer than the inclusion phase. Then one more thing is, and again, it is going to be a very good exercise to play with. Again, to relearn the concept of what we did. I try the same exercise with a cylindrical inclusion. Okay, cylindrical inclusion means right now my inclusion was the shape of a sphere, but try and play around with the inclusion which is of the shape of a cylinder going through and through. So that will simulate the case of a fiber reinforced composite. Okay, so fibers are in a shape of cylinders, so it will look something like this. So it has some fibers at the corners as well. Assume that we don't have any fibers in the corner. Just draw this center part. Okay, so this will give you the practice for fiber reinforced composites part as well. So in that case, you can select the properties of carbon fiber for the carbon nanotube properties. Look for them in the library for the fiber phase, or the glass properties for the fiber phase, and any epoxy properties for the matrix phase. Okay, and play around with different volume fractions. Again, if I go back there, if you are only plotting this center fiber, you can exploit the geometric symmetry here as well. Okay, so try and play around with that geometric symmetry and see how the results compare with the particle reinforced composite. So what we did today was a particle reinforced composite. This is going to be a fiber reinforced composite. Keep the volume fraction same and see how the results compare. Which one is better to play around with. Okay. One more thing that you can do, instead of having any inclusion, just remove the material at all. Just create it as a void. This will, with this way, you can simulate a ductile failure and see how a ductile material behaves, because from the elementary material sciences, we know that the ductile failure happens as a result of void nucleation and growth and then coalescence. Okay, so assume that void has already been nucleated. So create a spherical void in the middle. So you can create it by removing the material rather than cutting the material. So if you remove the material or remove all the material using the cut option, you have a void in the middle. Apply the same kind of boundary condition and see how the material softens as the void grow. Okay. So these are some of the practices which you can do, and I assume that you can do a lot of meaningful research, since the idea of this whole exercise was to give you some tools to do some meaningful research out of these tools. So I hope that it will help you in one way or another. I will upload today's session. Today's video will be uploaded on the Slack channel. If you are not already there, go and get yourself added to that channel, so that all the updates I post or somebody else post is going to be there, so we can discuss the research you are doing and the problems you are encountering, or if you are finding any issues, any things in conducting the exercises, you can share there as well. What else? I think that's that. If any of you has any question, you can ask now, or we can sign off and you can ask the questions in the Slack channel. If you need any help regarding, if you were doing what we did today, if you were doing it right now simultaneously with me, and if you're stuck somewhere, you can ask, you can stay back and ask me. I can help you with that. I'm going to stay here for another 5 minutes if you have any question. Otherwise, I'll leave the meeting after 5 minutes. So that's all. Good luck. We won't have any more FEA sessions. But if you want, and if there is a popular demand for it, we can have some more sessions. Otherwise, you can always take help from me in the coming days. Thank you so very much. And my email address is already there. If you're not on the Slack, you can always send me an email. All right. Thank you so very much.